So this video is an introduction to solving by factoring. And at this point, you're probably wondering, what is the point to factoring a quadratic? Why do we need to do it? And why do we need to know how to do it in so many ways? Well, solving by factoring really goes back to the idea from the beginning of this unit when we talked about the graphs. Now, when we graphed the equation y equals x squared minus 4, we got this parabola shape that crossed the x-axis at -2 and +2. Now, another word for x-intercept was zeros, because it's where the y value equals 0 for this equation. We also called it the solutions, and that's really why we need to factor. When I factor this difference of squares equation, I end up with factors of x plus 2 and x minus 2. You'll also notice that that's exactly the points where this graph crosses the x-axis. Now, how am I getting the values of -2 and +2? Well, really what we're doing with these factors, because it's where the graph crosses the y-axis, because it's where the graph crosses the x-axis, it's really where that y value equals 0. So what we're doing is we're applying the zero product property, which says that if two things multiply together, which our factors do, then the only time it's going to actually be equal to 0, the full product will be equal to 0, is when the first factor equals 0 and the second factor equals 0. Solving this, that's where we get the values of -2 and +2 from. Oops. It's really from the x-intercepts on the graph, or what we're going to do today, setting each factor equal to 0. Now the key here, the reason why it's called the zero product property is because we need to make sure that these equations actually are equal to 0 before we do anything else. Okay, before it didn't matter what the order was, now we need to be sure that it's actually equal to 0. Let's do some examples. In the first example, we are equal to 0, so we're all set to try and factor this. Now, there are some questions that we have to ask ourselves. Is there a GCF that I can pull out of every single term? Unfortunately, not this time. We also need to ask ourselves, am I able to factor this by grouping? Not enough terms for that either. I would need 4 things added on the left, and I only have 3. Is there a special case, like difference of squares or perfect square trinomial going on? Unfortunately, we don't have that either. 10 is not a perfect square. So our last option is the AC method. So that's what we're going to apply to this problem. Now, to do that, we need to multiply A with C in the top, so 1 and 10 in the top. And we have to write our B term in the bottom. We're looking for factors of 10 that add to +7. I can think of 10 and 1, 5 and 2. Now 10 and 1 won't work, but 5 and 2 will add to +7. So I'm going to create my factors using +5 and +2. When we're solving, because it was equal to 0, I can set each of these factors equal to 0 separately. When I solve these two separated equations, on the left I end up with an x value of -5. On the right, I end up with an x value of -2. These are my two solutions to this quadratic equation. Let's try example 2. Asking ourselves the same questions as above. Can I pull out a GCF? Nope, no common factor between 9 and 49. I can't factor by grouping either, but I do notice that this is a difference of squares problem. which is good because I can use my shortcut to factor it. It's also equal to 0, which is good, so I don't need to do any rearrangement before. Now, the difference of square shortcut says take the square root of a and the square root of b and use them to create factors. So what I'm going to do is I'm going to create two factors, 3x plus 7 and 3x minus 7. Because we're solving, this entire factored form is equal to 0, and then I can set each one equal to 0 separately. Then I'm solving these two equations to get values for x. On the left, I get a solution of negative 7/3. Don't be scared by the fraction. And on the right, I end up with a solution of positive 7/3. Both of these would be the x-intercepts if I were to graph this equation. If you want to, you can go ahead and use Desmos to test that theory for yourself. But not only would these be the x-intercepts, these are the solutions that would make this quadratic equation equal 0. Let's try another one. Can I pull out a GCF? No. Can't factor by grouping. It's not a special case. This one is another AC method for factoring. So again, we're equal to 0. I don't need to do any rearrangement. All I need to do is multiply A with C in the top and put my B value in the bottom. Now I want to list all possible factors of 30. I'll worry about the negative sign later. I can think of 30 and 1, 15 and 2. I can think of 3 and 10, and 5 and 6. Now I want to play around with the negative sign. They need to multiply to something negative. Only one side of this can be negative. Let's play around with the right side holding all the negative signs. 30 and 1 doesn't work. We won't end up with a positive 1 when adding them together. 15 and 2. I'm either going to get 13 or negative 13, so that won't work. With 10, I'm going to get positive 7 or negative 7, still not going to work. So the magic combination is 6 and 5. Now it's important that the 5 carries the negative sign. That way, when I add positive 6 with a negative 5, I end up with this positive 1 B value. Positive 6 plus negative 5. Now our A value was a 3. So I need to make sure that I divide that A value back in, simplifying when I can. With the AC method, we always rate our factors bottoms up. So I'm going to end up with x plus 2 for my left factor and and positive 3x minus 5 for my other factor. Because we're solving, I can set this equal to 0 and solve each factor set equal to 0 separately. When I solve the left-hand side, I end up with a solution of x equals negative 2. When I solve the right-hand side, a little bit more work involved, I end up with a solution of x equal to 5/3. Both of these would be x-intercept values of this graph. You can go ahead and check on Desmos graphing calculator to test that theory if you'd like. Let's try another one. Looking at this, is there a GCF that I can pull out of the whole thing? And there is. Thank goodness it's equal to 0 as well. we can go ahead and pull out an x from the whole thing. When I remove that x value outside, I end up with 2x plus 7 within. And we're solving this so we can set each factor equal to 0 separately. On the left, we end up with just x equal to 0. That GCF on the outside, because it was a variable, gives us a solution. We also need to solve 2x plus 7 equal to 0, which is a little bit more involved. We end up with a second solution of negative 7/2. These would be the x-intercepts if I were to graph that equation. Let's try another. First check is that it's equal to 0. Now we're going to see, is there any special case or GCF or anything like that? I could pull a GCF out of the whole thing. I could pull out a 4. But another thing that I'm recognizing is that this is actually a perfect square trinomial. Four is a perfect square. 36 is a perfect square. And this middle term is 2 times a times b. So I can use the perfect square trinomial shortcut. The middle term is added, so I'm going to use addition in that factor. A times x plus b. And that factor is repeated. Now, because this is a perfect square trinomial, when I set this equal to 0, I'm actually only going to have a single solution. It's just that that solution happens to be repeated. So I'm going to set 2x plus 6 equal to 0. That's really my only factor. It is repeated, but I'm going to get the same solution if I solve it again. So when I end up solving this factor set equal to 0, I end up with an x value of negative 3. This is the only solution or the only part of this equation when graphed that will hit the x-axis. It will only hit the x-axis at a value of negative 3. And if you don't believe me, take a second to graph it for yourself on Desmos. I have one more. Now, the last problem that I want to do in this video is a problem where the equation's not equal to 0. But that's a really easy fix. All we need to do is move this negative 5 over to the left-hand side so that the equation becomes equal to 0. So we just have to do a little bit of rearrangement before we go ahead and factor it. Now, there's no GCF that I can pull out, nothing to factor by grouping, no special case, so this is another AC method problem. I want numbers that multiply to positive 5 and add to positive 6. The only factors that I can think of are 5 and 1. If both of them are positive, we have our factors correct. They will multiply to positive 5 and they will add to positive 6. So I can go ahead and create my factored form. Solve when each factor is equal to 0. And I end up with solutions of x equal to negative 5 and x equal to negative 1. We will cover more examples like number 6 in our next lesson, but this is just an introduction into how we can solve different quadratics using our methods of factoring.